Hello everyone, welcome to my talk. So in this talk I'll explain a little bit what I've been doing the last year, part-time. I've been working with Dimitri in looking for transfer the MySQL application to actually use glibc. And I'll explain throughout the talk a little bit of the structure of glibc, not of glibc in particular, but of allocators in general, what they are, show a list of allocators, but go a little bit in broad overview of the concepts of allocators, such that everyone can follow and understand. And then eventually I'll explain, I'll show the results of that we obtained in MySQL before and after, and what I was actually able to do in order to mitigate those problems or the inefficiencies. So all allocators are expected to have at least two functions, the malloc and the free, and more. But focusing on these ones, what a heap allocator actually must do on a call to malloc would be to verify if it has enough space, and if not, it would actually request the operating system to allocate more space, either through memory mapping and getting new pages to use, or increase the data segment for the current program using SVRK. They all keep an internal state within the memory that they allocated themselves from the OS or in the heap, okay? And update the internal state of the heap in order to return the memory object, which would be the part, the individual, the unit that the application requested, which cannot be intermissed. So you cannot do pointer arithmetics with it. You cannot, from one, obtain the other, because you cannot expect that one memory object that was returned by a malloc would be consecutive to another. So this is the basic fundamentals. On a free call, you actually do the reverse. You say to the allocator like this memory object that I obtain, I want to get it freed. And so the heap allocator is responsible to update the internal state. And since it obtained the memory object back, it would try to reconsolidate the heap in order to free memory. And if it actually can reconsolidate, it will actually shrink the allocated memory space. So every allocator, or at least the ones I know, have this concept of arena, which is the main structure that governs the whole allocator. And the arena is responsible for doing the mutual exclusivity in the case of threading and so on, and is responsible to connect or to interact with the operating system in order to request heaps. And the heap would be that the memory itself that it allocates, right? The ones that it's obtaining from the operating system. Within the heaps, the header of a heap would be actually the internal state of the allocator, which would contain information of the next heap and so on, okay? And the chunks would be the end of the heap. The chunks would be each individual part, and either they are freed and they like in the lower part of the slide, you see metadata in the first free chunk, which actually might be bigger than another chunk that would have has been allocated. So the allocator might be using part of the chunk data in order to add information that would allow it to the allocator to actually navigate, so being more memory efficient. Usually, in the end of the heap, you'll contain a U chunk, which is the part of the heap that was not yet used for doing memory allocation. And then just moving on and explaining more the concept of the arenas and these structures, right? The arenas would have two main structures, or a typical arena would have what we call fast beans and regular beans, per se. This is a term that I use here in these slides, but they are not actually used in glibc, for example. And the regular beans would be for bigger size allocations, and the fast beans would be for smaller ones. And the characteristics of that is that the regular beans would be, in the case of glibc, they could contain a double linked list. So one of the lists would allow to traverse through all the sizes of allocations, while the other list would allow to traverse through the chunks, which are the units with the memory objects, and in this particular case, those that were not allocated, that have been freed. And to the second linked list is actually to navigate through all the sized ones. Usually you just take the first one, and usually when you free, you just put it in the head of that particular linked list.
These are all free memory, not allocated, right? And once
yes,
they're allocated,
yes.
They're removed from these lists.
So, yeah, exactly. So
Right.
well, these bins only contain data that has been freed, not data. Well, they would contain one chunk, which is no, sorry, you're right. So there's the top chunk then,
Yeah.
the top entry in the arena, which would contain the chunk that is the whole memory, which is the non-allocated memory, or never been used memory. So when it gets freed, it actually either is placed in a fast bin or is placed in a regular bin. Okay. So now we introduce threading, right? And it's not every, but allocators tend to say that threads are associated with arenas. And when you do an allocation, you actually, when a thread is created, actually assigned to an arena. Usually the first threads would contain their own arenas. That might be configured. In the case of the diagram, you fix it to a maximum arena of 2, and then the threads will actually share the arenas. This creates like some contention, right? Two threads cannot allocate memory at the same time. They have to wait for each other, right? But at the same time, having multiple arenas will actually allow you to reduce a little bit of the contention, right? If you create more arenas, you obtain less contention, right? But there's also the overhead of all the headers that you put in the arenas, or in the heap in the particular case, because the structure content of the arena is actually within the heap, and you waste memory. So yeah, at the last point, like just saying that each arena would actually allocate from each thread only allocates it from an individual arena and not interchanging. However, in C programming or many other programming languages, nothing guarantees that another thread will free the memory allocated by the other thread. So in that case, you might have a lot more contention because one is allocating and the other thread is freeing. And this, sorry, I'm a little bit lost now. So this allows the interchange allocation. Yeah, so this creates the problem that you have even more contention than you actually initially expected, right? So in a sense, some other allocators actually have a different strategy than the arenas for the contention, and to deal with the parallelism or multi-threading. And in these slides, I have another step. In order to reduce this contention, there's the notion of T-cache. And the T-caches are basically function like memory caches in a sense, which they keep closer to the thread, the chunks that they have themselves deallocated or freed, right? And that improves the performance because most of the time, a free or a malloc will never have to go back to the arena and create the contention of everybody trying to access the same arena per se. And this significantly improves performance, but on the other hand, might create fragmentation because they will be holding pieces of data or parts of the heaps that if they were given back to the arena, they would be able to consolidate and free and reduce the memory usage. Other allocators would actually use a little bit of a different strategy. Instead of using the arena to actually do the contention control or the mutual exclusivity of the arenas, they have a middle ground or middleware coordinator per se, which would keep track of what is trying to be accessed, and instead of actually use the arena as the unity of mutual exclusivity, they can use the heap or even some different regions of memory, reducing the contention and creating less performance problems with that. Also, what I think they also should coordinate is actually, once they realize that a T-cache is actually holding data that doesn't allow them to start freeing memory, they should interact with the T-caches themselves in order to say, hold on, if I collect this thing back and I can free data. And so they would reduce the initial problem of T-caches of holding the data for too long. And it would allow to simplify the problem of the allocation. So, and this, I think, is a few of the strategies that other allocators more specialized to threading are actually doing. Just as an example, like this is from a benchmark, from the GitHub page of a benchmark. Yeah, I know. So this comes from a GitHub page from my malloc bench, and it's just the list of allocators that they support. And so, just to refer a few, we have glibc, right? glibc is mostly the main focus on glibc is to get performance on these short-lived applications that would just start, and after a while they deallocate, and a few memory leaks or a few usage of memory is not such a problematic thing. So they are kind of good for those kind of scenarios. On the other hand, G or TC, malloc, right? They were more meant to many-threaded applications and to the cases where you actually would have a lot of contention for that. So, and just to say, I kind of see these as a problem of optimization where you have performance versus size, but not only. So the more you actually try to increase the size of your, the more you try to obtain performance, the more penalties you probably have in the internal state of the. You have to allocate, you have to have more data because either you're creating more threads or you create more mutexes in this middle coordinator in order to split the data. So it's a trade-off between overhead in size or overhead in performance, right? And I see this thing with 3 dimensions, like the allocation profile of the application, right? It really depends on the application. How much threading does the application has? Or the particular allocator, was it meant to be used in threading or was it meant to be used in single-threaded applications and so on? So there is a lot of possibilities or of trade-offs per se. So I think I'm speeding a little bit, but it's okay. So for this example that I have in the MySQL, and this data was obtained by Dimitri, right? It took a while before I actually gave him the reason that there was a problem in glibc. Initially I thought it's impossible. It must be some issue there. There must be a leak in your application. No. Up to the point that I myself went and I took the data. I see how is it possible, right? And in the many experiments I did, enabling, disabling T-caches, changing a lot of the tunable parameters in glibc, I got to the conclusion that, yeah, max arena equal 1 would actually show different results, and the one that popped to my eye was really the VM size, which in glibc was huge, and this is because of all the arenas that it was creating with the default parameters, right? It was allocating way more memory than you actually would use in the end. But it created the side effect that the RSS would not stabilize. Somehow there was some sort of fragmentation there or internal leak that would keep growing and growing the RSS. And so we...
What are we looking at exactly? The right, left side, right?
Yeah, so on the left side we have the default Max Arena as glibc has, right? And on the right side we actually fixed the Max Arena to a single arena. So there, in this case, you would have a lot of contention on the allocation, right? Every malloc is fighting to get data, right? And on the left side, they don't. They have a lot of performance. Sorry? No. Oh. I understand the question. So what we're seeing here is a loop of. So it's a repeated pattern of clients connecting to the database per se, and you see the ramp up because they are creating less threads, and then they create more and more threads because more clients are actually connecting to it. I don't know precisely the number of threads connecting on the upper bound of each one of them, but it's a lot.
I'm just wondering how you change Max Arena without restarting MySQL.
No, we actually restarted MySQL, right?
Okay,
so they are continuous because actually Dimitri has his own software to actually collect the data, and he gets the parameters even though the application restarted and so on. So he could present, he just executed the first one and closed it, initiated the second one, and then he cut it the graph and put it side to side. So.
It's the system memory, not the process memory.
Say again?
So I take that the total system memory, not the process, the MySQL
It's MySQL.
It's MySQL? Oh,
Yeah. It's only MySQL. It's not other processes.
So the MySQL daemon was restarted at 11:10. It's not one heap.
Yeah,
It's
so
one heap state.
don't
The heap was restarted.
don't see it as a single execute. Imagine that we glue two graphs, okay? We didn't actually execute one single iteration. We executed twice. It's just for the practicality, it's easier to show in this way, okay? So, but as you could expect, I guess, like executing with Max Arena is really bad. So we had a performance drop of a lot. So they immediately told me, yeah, you know what is this Max Arena 1? It cannot be. And I said, hold on, this was just to prove the point, because I need to understand what was happening. And now at least we have an idea of why we differentiate so much from other allocators. And so, yeah, basically we realized that, okay, Max Arena actually gives much worse. Max Arena 1 gives much worse performance, and we cannot just use it as is, of course, but it called the attention to a problem in malloc infrastructure, which was that T caches are limited to 1 kilobyte blocks, and we were trying to allocate much bigger things within MySQL. So the solution was actually to, before that, actually, I have another slide, which is a comparison between TC malloc, two different versions of TC malloc, and the behavior of the default glibc with Max Arena to the default value. And you see that the RSS keeps growing, as we've seen before, and the VM size is double what the other allocators do, right? TC, in this case, TC malloc. It's kind of the same execution pattern. Maybe the values, you cannot correlate one execution to the other because they were either executed in a different month and the infrastructure was a little bit different. The values were not comparable per se. So yeah, this is not only a problem of MySQL. It has been reported in all other softwares, and what we've seen is that they usually tend not to fuss too much about having glibc fixed or having it investigated, or even themselves to go and investigate the problem. They simply say, okay, I have other allocators, I'm going to use them. I can simply use them. This actually brings a problem, is that most of the times they They cannot rely on the versioning of those allocators. They have to keep copies of the allocators within the software, and they have to include those own copies, because from version to version of the allocator, they might identify problems. And that becomes a little bit unpractical, and they start to having old code. So these are two examples of, apart from MySQL, that have present similar problems. So what have I done? So I have submitted a patch that actually submitted, and by now is in version 2.42 of glibc, that actually allows to increase the chunk size allocated within the T caches. So T caches now can allocate up to, or can store chunks up to 4 megabytes. This is parametric. It depends if you set the tunable, because this feature is not fully done. There are other things that need to be fixed. So the way we do it is that in these T-cache entries, which is like similar to the bins, it's a list of linked lists of chunks that are in those bins, right? And the first 1 kilobyte, each entry of that array would only contain chunks of the same size. And this is actually to be maintained in glibc, because it allows you to just go fetch the first entry in the linked list and not having to traverse any linked list. But apart from aside or above 1 kilobytes, actually the strategy is to allocate regions of sizes. And the regions keep growing from element to element on the array in powers of 2. And this allows to actually store, so the further you go down that list, you'll have bigger data, but it's most likely that you have fewer elements per se. And in the upper ones, the opposite, right? You have smaller ranges, but because you grow in powers of 2, maybe you have it well distributed through all those linked lists. The other thing I forgot the point. So, hold on. Yeah, so basically the optimization is that. I mentioned that is configurable through the tunable, and you set the T-cache max for that up to the size that you want the T-caches to support. The missing part of this implementation is that in order to properly allocate, in the current state, each T-cache entry is allowed to place by default 7 elements, right? But 7 elements might not be enough, because now you have these entries that they don't contain all the same size. And if you fill those 7 elements, then any other frees that happen on different size, they will be just sent to the arena, and they will skip to be entered in T-cache. So I'm working on a strategy to actually surpass this thing. There's a question.
So why not make the new T-cache max as default? What's the drawback of?
So just because the strategy now is not good enough, it might be that in MySQL actually it worked well, as you will see soon, but for other programs it might be a problem, and it might be even worse, because what would be in my opinion, what we are trying to do is to reduce the max arenas in order to not abuse the memory usage, right? But if you reduce to a point and then the T-caches get filled up and then they stop being effective, then you actually get a big drop in performance. So we need to find actually a different strategy than this counter to assign chunks in. Once the T-caches are full, we have to start cleaning it up, saying, oh, this was not used, let's send it back to the arena. And that's what I'm trying to work on now, to get done to push to send a patch upstream. So the idea would be to I call it timestamping because it remembers timestamp approach, and I also do that in order to quickly compute which chunks can actually be freed or given back to the arena, which is like each thread will contain a number, which is a monotonic number that keeps increasing every time you allocate. And you'll have you'll have a different tunable that specify the amount of memory that you can have in each Tcache. And by increasing, each time you actually allocate, if you annotate the chunk with that timestamp at the period where the malloc happened, or when the free happens, sorry, it's not the malloc, when the free happens, you annotate it with that number, then you can, when traversing the list of entries in the Tcache, you can actually verify like, oh, this is an old chunk, so I'm going to send it back to the arena because if no one used it until now, it's unlikely that something will use it, so I'll give it back. And that would be more or less the strategy. So these are the numbers on MySQL after the execution. This was a much longer execution than before, right? And the intent was to see if the RSS would actually keep stabilized or if it would go growing and growing and growing. You would see a bump here, right? And that's the reason why I actually put this slide here, because the bump was an actual effect of an allocation happening within MySQL. So MySQL requested the data, not just some random glitch within glibc that actually required that. So the result, they were quite happy with the results, and they are looking forward to more improvements in glibc in order to actually replace tcmalloc to the default allocator in glibc. So, and the next slide is like the performance of the thing. So as you see, like in the previous slide, we had like 10,000 in commits per second, or around 11,000 commits per second in the best case. And in this case, we have 12,000, but well, again, there were improvements in the infrastructure, and so the results are not comparable. What we identified was that it was just a difference in the environment, and then it would just be faster. So, but the results of this run were actually hand in hand with Max Arena being the default one, but in this case without the RSS problem. So this is my last slide. I don't have a conclusion slide, but just to say that the point of the presentation is not really to show off what I did, right? It's more to call the attention to the allocators being all these aspects of the allocators, and that there is plenty of work to be done in this area, and that yeah, we should try to actually go to the next level of allocators and try to be able to bring glibc to a level which can compete with all the other allocators, and I think it's feasible. And yeah, then I think it's done. Thank you. Questions?
Probably comes from my not very deep understanding of the malloc implementation.
Yeah.
But if I understood correctly, you have one arena, and then you have this large Tcache allowed for every thread. So to me, somehow it seems almost like each thread has its own arena, which is the Tcache.
Yes.
So have you benchmarked or tried out with just like the one arena per thread? And
we did benchmark, but the whole point here in this particular case of MySQL was not like the performance, was really RSS. So the more arenas you have, the more you have the problem that the memory consumption would grow higher and higher. Okay, so I can go back. So the problem here is actually this grow here on the RSS for the default number of arenas. Okay, so as long as you have two arenas, you see this behavior. And I forgot to mention, so this they interchanged to tcmalloc because they identified one environment where the customer complained. The customer had very little resource for the machine, or if it's virtual or not, I don't know for sure. And they kept complaining that MySQL was crashing from every week or so. And so they went to analyze and they verified that memory consumption was constantly growing throughout the week. And then the application would get killed and restarted automatically, right? It can recover, but it was constantly growing and crashing, constantly growing and crashing. So that's when they realized that glibc had a problem, right? And they switched.
So if I understand, even if you have two arenas, this starts to happen, basically.
Yes.
I kind of missed that detail, okay.
Yeah. I looked into that. I thought that my thought was like, okay, we have a RSS growing, but at some point it will stabilize. But where? I didn't know where. It could be 2 months or something, right? And then by reducing, I reduced to arena, max arena 2, and then but still it was growing and growing, never stabilizing, which yeah, it didn't help.
So looking at this, my guess is that the reason for the RSS growth is fragmentation, right?
Yeah.
So, and you've solved that essentially by keeping larger chunks around so that you're not allocating lots of smaller chunks and fragmenting.
And
Your
they don't get
arenas,
consolidated, yeah.
So if you were to somehow just segregate the arena allocations a bit more, keep the smaller chunks in one part, the bigger chunks in a different part,
Yeah.
would you be able to resolve it perhaps without having to
Yeah.
increase your caching so much?
Yeah, that's kind of like the topic of yesterday hallway discussion, is that it would actually make sense to have two memory spaces where you allocate, one for more volatile data that you free from time to time, the other one for the more long-lived one, in which you don't want to actually fragment and keep stable. So
We've tried marking long-term allocations in the kernel, and it never
Yeah.
works because people never know
yeah,
what's really
it's,
long-term.
yeah, maybe that might be a problem.
A stupid approach that springs to mind. A stupid approach that springs to mind might be to keep existing arenas as they are, but simply start the search for new chunks at a point in the arena which depends on the rough power of two of the size of the allocation. So small ones start from the start, ones twice that size start from some way in, and so on and so forth. So that. In effect, this would in effect segregate allocations by size as long as the arena isn't too full. Without needing to actually split the arena up and increase fragmentation.
Yeah, but I don't think
Maybe.
you can easily control that. In the way, at least the way it is developed, right? You have one big chunk in the end where you cut in pieces, and then it's consecutive. You go from the start to the end. You don't fragment in the middle or anything. So what I think you're suggesting is like to break the arenas like half apart, and then you start.
Yes,
you
start looking for free space
basically
in the middle or to 2/3 way toward the end or something. It's fiddly, but
it's tough. Yeah, the way I see other allocators actually doing is that they allocate a bigger chunk per thread, and then they can have whatever fragmentation they have there. It doesn't matter, because once the thread gets freed, that chunk is returned. And then instead of having small pieces of fragmentation, you have a bigger chunks of fragmentation. Or you have bigger sizes, and then you can break those apart. But as long as you keep one max arena, there's no thread there's no one thread that goes to attempt to malloc from that arena or that arena, right? The problem is that when you start to have more than one arena, if you want to allocate a smaller chunk, you actually have to go to the arena that was assigned to you and not to the other one that already has fragmented parts that would fit your needs. So that's my feeling on why we get this continuous growing after max arena 2. But even though I cannot understand how the fragmentation happens forever and ever, when max arena is equal to.
Two things. One is there are page-based allocators that use size classes to solve some of these issues. glibc, being ptmalloc based, is heap based. conceptually it has a logical heap that keeps growing. And when you have a logical heap that keeps growing, it's optimized for locality of use. And when you have that and more than one thread and more than one arena, temporal use can in theory cause infinite ratcheting between two arenas. Because whenever you go to try to reclaim or free, you are unable to because the top chunks are in use. And even though later they're freed, maybe your thread is already bound to another arena, the free that you have is never going to get reused by you. And we see this often when you have a producer-consumer thread workload where memory is being handed from one thread to another thread. That thread does the free, but never the allocation. And so that can at times cause ratcheting. One question I would have for you, which would be an interesting evaluation, is we permanently bind the thread to the arena. And in doing so, prevent it from possibly allocating from another arena.
Yeah.
So a concept that had been discussed between, I think, the Mathieu Desnoyers and myself, particularly looking at the Linux kernel and generic allocators like these, is what you really want is like a per CPU arena, and that per CPU data basically gives you a constant CPU number. And when your thread is executing and the kernel scheduler puts the thread on that CPU, you just look up the arena that's local to the CPU and you get memory. And the hope would be that in doing that, like if you had a producer-consumer workload where both threads were on the same CPU and there was swapping between an SMT unit, they're both going to access the same local memory, the same local arena, and therefore you get perfect handoff of that one arena. And so rather than having the threads bound permanently to a singular arena, you now have the threads that are on that CPU are on that CPU's arena. And if those threads migrate, and likely if they're a producer-consumer, maybe they migrate together to the same CPU, and then it kind of becomes a question of like, how are the threads with the locality of the arenas they have? Have you looked at anything about
No, I didn't.
unbinding the threads from their
I didn't.
bound arenas? Okay.
I did not. One thing I see in those scenarios is that threads are also not fixed to a CPU, right? They can change CPU. And so when you free actually on a different CPU, which is assigned to a different arena, you should also return the memory to the original arena, not to the original CPU. So there will be contention in any case, right? And the threads come in the middle actually to retain that thing. So I mean, when I say threads, I want to say Tcache. Tcache is in the middle to actually disable you to actually return to. So it has to be manipulated as well. It has to take into consideration that.
Yes, you mean like if the arenas were bound with CPU and you do a cross CPU free, we could solve it. And there was an experimental post to the list about using URCU wait free queues, so that when you free, you basically wait free and queue your free to the remote arena and you just walk away.
Okay.
And I found that was really interesting because often by the time you've taken the lock and you're about to look for things, you can then process all the wait-free queue data that's been given back to you. But again, it's just more work.
Yeah. There's plenty of work to
Cupertino,
be done.
there are decades of work that we can do in this space.
In no way I'm saying glibc is not good at all.
Yeah.
No,
No,
I'm
yes,
saying quite the opposite.
So,
So not the other way around. That's what we want to do.
I agree that there is without perfect a priori knowledge, it's very difficult to get what is effectively a one-dimensional bin packing problem solved efficiently for your application. And I think that's why so many other mallocs exist, because they are either more geared to a particular workload than this, but we want to have a general purpose allocator and we want to try to maintain one that works well for a lot of workloads. This is really interesting though.
Yeah.
I'm curious how we're going to solve this. I look forward to it.
Have you published instructions for reproducing?
We did not. We have a blog. Soon enough, I'll post a blog, and I'll add the information for reproducibility. Yes.
Okay, so
I need to make sure that we can publish the MySQL and how to probably correctly point you out to that, but we'll publish a blog on the subject.
it's like the data set that we need to load onto MySQL.
Yes, maybe I don't know. I have to see if we can share the test infrastructure and so on. That's something I didn't ask.
Yeah, I
So
mean,
it will need to be. Dimitri will need to help me out fill that gap because I don't know the information.
yeah, it will be interesting to look at the heap data structure over time and see
Yeah.
if we can extract some statistics from that and
I
see.
really want to kind of use your tool to actually collect the information at different timestamps and then see at different points, but the ones that grow just a little bit, just to see what happened, which chunks actually increase it.
Yeah, I mean, is it one-way fast bins? Is it
Yeah,
Tcache cross arena obstruction or something like that?
Yeah,
Okay,
yeah.
thank you.
So one thing to notice is that in this test case, there are plenty of threads, and they are constantly connecting and disconnecting, right? So it could be some side effect on the thread infrastructure. I don't know. I'm just throwing ideas. I don't know what's the reason, but most likely, as John said, fragmentation is one big possibility.
So one wild idea is try to call malloc consolidate from time to time.
Yeah, we tried. It doesn't work.
It doesn't
malloc
work.
consolidate didn't solve a thing. Actually, I put malloc consolidate being called every 100 mallocs. I hooked malloc for that. No.
It seems to me, I mean, in this particular case, we were lucky enough to be working very closely with the people who actually had the problem, had the issue. And we know for a fact that these kind of applications that Cupertino mentioned, we know for a fact that what they do is that, we have memory problems with, I don't know, normal malloc from glibc. Immediately we go, we try jmalloc, and then we use it for a while. And then at some point, it stops working as well, because, I don't know, we have more threads or because whatever. Okay, we just try tcmalloc. And then tcmalloc seems to be working until it doesn't. So I think this use case shows that when there is like this good interaction between the people who actually have the problem and in this case, the glibc, I mean, maybe the best solution is to not just jump to the next bus, which is passing by, like tcmalloc or whatever, but actually make a little bit of effort to fix it. And maybe this is more for the glibc both that I will miss, but yeah. So how will it be possible to get those projects to make it easier for them to actually share workloads and to share, this? To motivate them to actually try to fix the problem instead of just hopping to something else.
Jose, I just want to comment to this, and I was talking to Cupertino about it, but fundamentally, we need better observability tooling.
Yeah.
And I gave a talk at LPC when it was in Santa Fe, and it was about a system-wide malloc tracer. And we did have one opportunity to work with a large customer where we ran the tracer, but the tracer was like an API level trace where we captured like API trace data. We could then take the trace data and run it in a simulator, and the trace data contained inter-thread sequencing, and it used a top-level global in order to get always happens before sequences with the mallocs and frees so that they're correctly interleaved. It's still super hard to do the analysis because what comes out of the trace is like 4 terabytes of trace data, and you rerun it in the simulator, and you still don't understand the state of the heap. And I think what was fundamental.
AI is for?
What was fundamentally missing, I think, was Florian's dumper piece, which is we were capable of getting a trace. We were capable of observing things. Like I could tell the customer, yeah, you've got 13 trillion 12-byte objects, and they're highly inefficient for the co-located heap metadata that we have in the allocator. And so it's just going to take a lot of memory. And they were okay with that answer, but I do think that trace, dump, analyze, like those pieces of observability, allowing the end user to observe the internal state of the system is so valuable and is the direction we should be going in, because without that, they can't exercise their engineering best discipline to determine what's going on in my system. And because they can't, they simply replace the black box with another black box. And we had the same question from the QEMU folks. So QEMU was using TC malloc for a while because, and I said, well, why? And they said, well, because it makes VirtIO go faster. And we said, well, why? And they said, we don't know. It was just a black box, and we substituted it in. And so Tcache, DJ's work on Tcache was directly a result of improving QEMU's VirtIO performance for these cases, because if I didn't do that, then our teams at Red Hat had to maintain 2 allocators. And I didn't want to maintain 2 allocators, so we just wanted 1 allocator. But I want to let people be able to replace their allocators. It's an important feature, but at the same time, we also need to understand our failure modes. And the interesting thing was the Google teams that were maintaining TC malloc are also very interested in observability tooling as well. And I think so is J malloc. And so I do think that there's an opportunity here for a collaboration across multiple projects. If you ever think of tooling, we should think of generalized ways the tooling would work to gather that data or observability.
Do you need a full trace? I mean, it sounds like
Yeah.
it sounds like you from your example, you just traced everything and just dumped the whole data raw, like you said you have terabytes of data. Could you do it more like statistically or analysis, like just record, okay, 12 bytes of data was allocated, 12 bytes allocated, and what was freed, and just kind of give a constant snapshot of how much memory. So you don't need terabytes of data, but you could just kind of have a running thing to give you an observability without the full.
Yeah. The reason we captured the trace was to attempt to recreate the state of the heap, because the state of the heap is the most valuable thing for a developer to know, because it shows you if you ran into a pathological case. So the pathological case could be like, so you're 100% correct. There's no black and white. There's lots of middle gray ground where so one of the key questions that, like when I see a graph like this, one of the key questions that I always ask the end user is, like, do you know how much you requested of memory? Because that graph is there, but there's not a graph of how much did MySQL request? Because if the request is growing and they're not freeing, then it going up is fine. But you actually need aggregate API data, so you need to integrate the incoming request.
So you can do it almost like a profile.
Correct. But you still need to integrate. So for every malloc that comes out, you integrate up, and for every one that it comes down, you integrate down. And so you need to have the integral, and then that way you can tell a user, no, you actually did request this much, right? Absolutely. So there's a middle ground for observability, which is integrating the API calls and figuring out how much they requested, versus full trace, which would give you. So the reason we wanted full trace is because I would love for anyone to give us a trace of their workload, and then we can store the workload traces. Why? Because what's going to happen is Cupertino will later come back and say, I got a patch to improve performance. And then I'll say, well, let's rerun that patch against the stored, saved workload traces. And running the workload traces is much easier than getting a hold of all the workload, setting up multiple VMs, doing the workload traces and doing those things. So we were hoping that that would help. But I still think we fell short because we needed some of the intermediate observability pieces.
Perhaps this is obvious, but another essential observability piece, which I don't think exists yet, is a way to diff heap dumps against each other and to get some useful output out in some way.
Florian for that, please. We need to talk on the heap dumper.
I know.
He was there. Yeah, but I think I did. I asked if two different dumps would be comparable.
Heap diff.
Yeah. Okay.
So I assume the MySQL uses thread pool inside, right?
Thread?
It uses thread pool inside MySQL.
I'm not sure. It uses threads. You
I
said
think
thread.
one
thread
thing
pool?
that would be interesting if to try to restart a thread periodically to flush out.
Oh,
the
but they are
Tcache.
restarted. The threads are for the clients that are connecting. So each client connecting to the MySQL database creates a thread itself, which are concurrently requesting the concurrent data and requesting more allocations and more allocations. So I don't know if I'm answering your question.
Okay, I'm a bit confused. So is this, I assume this is the MySQL server process that we are
Yes,
looking at.
it is. So each time you see a bump like this, it means lots and lots of threads being created and freed. Lots and lots.
Inside MySQL process.
Inside MySQL.
Not the clients connecting.
Yeah. This lower bar here in the bottom is actually for the fewer threads that when you have fewer threads, then you actually can make an impact on the allocation. You don't need to allocate more for those amounts of threads. It gets to a threshold that you actually start allocating more. And then in the end, you reset to 0 threads. You'll grow from just one single connection, and then 100, and then 1,000, and it keeps growing, and that's what you're seeing here.
Okay. So the MySQL process, MySQL server process itself doesn't have a permanent pool of threads that are just sitting there waiting for
I'm not
work.
sure of the internal.
Because that's the typically how
the
it's
typical,
done, right?
I don't know. I don't know for sure.
Yeah.
I don't know if each connection would actually connect to an existing thread or not, but I presume it doesn't. I think it gives back the thread to the Max Arena, to the arenas per se. Any other questions? I think we are kind of on time as well, 5 minutes to the hour. So thank you very much.